Enough, we started out section 5.3. We covered the fundamental theorem of calculus part 2. So now we're going to go back and cover the fundamental theorem of part 1 in the second part of this video. Now, I'm going to hint at that this way by calculating this. It's not often, or it's not unusual to define a function in terms of an integral. So what would that all be about? Well, it's just an area underneath a curve or between the curve and an x-axis for a function, and depending on the upper limit of that integral, like in this case b, you're going to get an area, and that area is going to depend on what that limit is. But if this is a b, then this becomes a function. So wow. And in fact, you can see that this function has a maximum right about here where the graph touches the x-axis. After that, what happens to the area? Yeah, you get an assigned area which is negative, so it's going to start detracting from the total area. But nonetheless, it is a function, and right here we've got a function of the upper limit of this integral, x. We're going to evaluate g prime a couple different ways. So first of all, let's calculate g prime of x using the fundamental theorem of calculus part 2, which is what we covered in part 1 of this video. So let's see. That's going to be, well, I need an antiderivative for t to the fourth. Suggestions. What would be an antiderivative for t to the fourth? Yeah, t to the fifth over 5. And that's going to be between 1 and x. So, okay. Let's calculate that. That's going to be 1/5 x to the fifth minus, 1 to the fifth is going to be 1, so 1/5. So yay. There's our function, that's g of x. Well, then we're asked to find g prime of x. Well, g prime of x is going to be the derivative of this. I'll let you put on your thinking cap for a second. What's the derivative of that going to be? Yeah, x to the fourth. Because the 5 and the 1/5 are going to cancel. Derivative constant is 0, so x to the fourth. Now let's look back and see if there's kind of a shortcut. And you might notice kind of a little bit of a similarity between our answer and the integrand. Do you see kind of a little similarity here? We end up with x to the fourth. Take a look at the integrand. It's just t to the fourth. So the fundamental theorem of calculus part 2 just says, well, when you have something like this, you can just drop this in to the integrand, and that's going to be the derivative. It really reflects the fact, also seen in part 2 of this, the fundamental theorem of calculus, that the derivative and the integral are inverse operations. What one does, the other one undoes. So if you differentiate an integral, well, especially one like this, all you're going to get is just this variable plugged into here. So it's going to be x to the fourth. So that's it. It's kind of a nice little theorem. It's kind of odd that it's called the fundamental theorem part 1, because we use the fundamental theorem part 2 so much more often. We use the fundamental theorem part 2 the way we calculate it here. But fundamental theorem part 1, I think maybe historically the fundamental theorem part 1 led to the discovery and use of the fundamental theorem part 2. But in any case, let's move on down to example K here. This time we're not going to bother trying to find an antiderivative here because it would be a lot of work, if not impossible. In fact, I think it probably would be impossible. In any case, we want to know what g prime of x is. So this is a perfect case for the fundamental theorem part 2. This should be an easy couple points on an exam. Go ahead. Tell me what it is. What's g prime of x going to equal? Done. Ding, 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 ding. Wait a minute. Should have had this out.
That was easy.
Yay. Sweet. Sweet. Now, one little thing to mention here, if this is something other than, you know, just an x or a y or whatever variable, if it's like an x squared or a sine, then you're going to have to use a chain rule. So it'd be the derivative of the function, or it'd be this times the derivative of that function. So if you have something up there that's not something other than just an x or a y or whatever you're differentiating with respect to.
Do you have an example of that in here?
Sure. I don't have one in here, but let's just make one up. Let's do h of x would be the integral from 2 to x cubed of e to the 4x squared. Actually, I don't want to put x there. I want to put a t, I suppose. I got a t. I'm out.
Just make the left side of the x a curly.
Yeah, that's all right. I'll just make that a t minus 2t dt. So when you differentiate this, h prime of x is going to be e to the 4. I'm going to put in x cubed here. So it's going to be x cubed squared, which is going to be x to the 6 minus 2x cubed times the derivative of x squared, or x cubed. What's the derivative of x cubed? 3x squared. So there's your example. Yeah.
I did why from x cube and 3 and 8.
I'm sorry, I couldn't hear you.
How the x to the power 3 is in the limit?
I just gave another example problem, so I chose this. Okay, so it wasn't something that was on the sheet, but Christian asked for another example. Okay, one last one that's something you might see in the homework here, and it is to estimate the area of something like this. So f of x equals sine of x. They ask you to do a rough estimate of the area. And I guess I'd break it up kind of like this. I'd break it up into 3 little parts. So what would you do to find the area? What kind of things would you do to find the area of y equals 7 sine of x? If you're going to estimate it with these 3 rectangles, I guess what would you have to know?
The width and the height.
All right. So the width would be pi over 3 for each of these, right? Because they're all the same. How about the height? How are we going to find the height? James got the width for us. Well, it seems like the height is being judged right here. So how could I find the height of the function at that point, or the height of the rectangle at that point? It's not pi over 6. Pi over 6 is the x value. The height would be the y value, right?
Well, yeah,
Yeah, so we're gonna plug it in. So sine of pi over 6. Now this might be one that you remember, maybe one that you don't. Does anyone remember what the sine of pi over 6 is? All right, lots of blank stares. That's okay. It's early in the morning and it's raining.
Is it root 3 over 2?
No, it's not.
I guess.
All right, but good guess. Now calculus is done in radians. So your calculus should be in radians. So let's do 7, or excuse me, sine. I'm going to skip the 7 part. Sine of pi over 6 is going to be 0.5. So bam. And then of course times your 7, you're going to get 3.5. So the height there is going to be 3.5, which seems to match this right here, 3.5. Of course, these two are going to be the same, because sine of 5 pi over 6 is also going to be 1/2. So the last one we need to determine is this one right here. So let's see, what's that one going to look like? Let's see. Well, looks like the sine of pi over 2, right? Let's see.
I'm guessing.
Yeah, sine of pi over 2 is going to be 1. So they're going to be pi over 2 and 7 there. So we can find the areas of all three of these things. It's going to be 3.5 times pi over 3 plus 3.5 times pi over 3 plus pi over 3 times 7. Let me just kind of write it out. I'm not going to try and be really cutesy with this thing. Let's see. Let's write out pi over 3 times 7 over 2 plus pi over 3 times 7 plus pi over 3 times 7 over 2. So, yay. A lot of nice arithmetic heading your way. You could probably make that a little bit easier if you factor out the pi over 3. Pi over 3 is going to be times 7 over 2 plus 7 over 2. This is going to total up to 14. So we should get 14 times pi over 3. Let's just check that out. 14 times pi over 3. Bam. There you go. I can't say I'm overly fond of making you do this kind of menial calculation. So if you run across it in the homework, what you could do is take one of the links that I have there for, let's see, chapter 5 should have a link for Riemann sums. And let's take advantage of that link right there. We're going to have to change our function. So our function is going to be 7 sine of x. And let's kind of zoom out a little bit so we can view that. We're also going to change a couple other things. The endpoints of our interval are going to be between 0 and, let's make this top one pi, pi. So that's looking better. And then let's see, I wanted 3 rectangles, so 1, 2, 3 there. Except these are measuring from the right-hand endpoint. I don't want the right-hand endpoint, I want the midpoint. So the last change to do is make that a midpoint method. And there you go. So with all those changes, let's go back up and see our Riemann sum. And there you go, 14.6607. So if you have to do it, then you can double check yourself that way before you submit your answers. Make sure you get them right. So let's put a QR code on this in case anyone wants to find that link later. And that's about it. Comments or questions on the little wrap up for section 5.2 here? Okay there? Looking good? All right. Hopefully should be some easy points for you.